Hello and welcome to today's webinar, Streaming Data Analytics with Amazon Kinesis Firehose and Redshift. On your screen, you will see a Q&A pod. Please submit your questions for our presenter and moderators at any time, and we will address them as they come in. At the conclusion of today's presentation, there will be several polling questions preceding the live Q&A. Please provide us your feedback when you see the polling questions appear on your screen. Today's webinar is being recorded. In the next few days, we will send you a follow-up email with the on-demand links to the presentation deck and the webinar recording. And again, welcome to today's webinar, Streaming Data Analytics with Amazon Kinesis Firehose and Redshift. Our presenter today is Ray Zhu. Ray is a Senior Product Manager for Amazon Kinesis. Prior to joining AWS, Ray had 5 years of experience in the business intelligence software and telecommunication industries. Ray holds a bachelor's degree in electronic and information engineering and a master's degree in business administration. Also with us, we have Alan McInnes and Tony Gibbs. They will be your moderators who will be engaging with you to answer your questions throughout the presentation. Ray, welcome. The floor is now yours.
Thank you, Heather. Good morning, everyone, and welcome to today's webinar session. The topic for today is Streaming Data Analytics with Amazon Kinesis Firehose and Redshift. So in today's session, I'm going to walk you through an example of using Kinesis Firehose and Redshift to analyze Maryland's traffic violation data in real time. And the purpose of this session is for you to get familiar with the setup and the data flow for using Kinesis Firehose and Redshift for real-time streaming data analytics. And as Heather mentioned, after this session, you'll have access to the recording of this session and also the decks. And I think you can use the contents within the deck as a step-by-step guideline for you to start trying out these two services with your own data and also the sample data we'll use in this session. So to start this session, we'll very quickly spend probably 30 to 60 seconds to give a quick introduction to the Kinesis Firehose service and the Redshift service. And then the main part of this session, we're going to walk through the 5-step setup for a streaming data pipeline from Kinesis Firehose to Redshift, and then using a visualization tool to run a query and visualize the data from Redshift. And again, in this session, the sample data I'm using, it's the Maryland's traffic violation data, and the data set is publicly accessible so that after this session, you can try it out yourself and probably do more interesting visualization on the Redshift query. So Kinesis Firehose is one of the streaming data services at the Amazon Kinesis platform. Kinesis Firehose automatically loads streaming data into Amazon S3, Redshift, and Elasticsearch services. You do not need to build any application or manage any infrastructure for using Firehose. All you need to do is to spend probably 60 seconds to set up a Firehose delivery stream through the console, which will be a streaming data pipeline pointing to your destination resource, and afterwards you configure your data producers to continuously push data into your Firehose delivery stream. Then everything else will be managed behind the scene by the Firehose service. And for today's session, we're going to focus on Firehose to Redshift. Amazon Redshift, it's AWS petabyte scale data warehouse where you can run standard SQL against for complex data analysis. So before we dive into the 5 steps for setting up this streaming data pipeline and analytical process, we'll give a quick overview on the data flow when we use Firehose to stream data into Redshift. So on the very left-hand side, you'll configure your data producers. And the concept of data producer are the entities that are generating data where you want to capture and analyze. So a data producer could be a web application server, could be an EC2 instance, could be mobile devices, or could be IoT devices. And you can configure hundreds or even thousands of devices to continuously and concurrently push data into the Firehose service. Now, sitting in the middle, it is the Firehose service, and that's the core service we're going to use here today for the streaming data ingestion. The Firehose service will capture these data from your data producers in a continuous streaming manner. Then on the right-hand side, the Firehose service will automatically deliver the data into the destination that you specify. And today the service supports Amazon S3, Redshift, and Elasticsearch service as the destination. And once the data lands into these destinations in a continuous manner, you can use your favorite analytical tools to query and analyze or visualize the data from these data stores on a continuous and real-time manner. Okay, let's dive into the step-by-step setup. So first, before we start the streaming data pipeline, we're going to set up a Redshift cluster with a database and a table in it. And we're going to stream the data into this particular Redshift table through the Firehose service. I'm going to the Redshift console and create a new cluster. Here I'm naming my cluster as Ray Streaming Cluster. Also create a database called StreamingDB. For the port, I'm using the default Redshift port of 5439. I'm also going to configure a master user and password for admin purpose to the Redshift cluster. Next step, I'm going to pick a node type. Here I'm using DC1 large, which is the smallest node on Redshift for this demo purpose. I believe if you are eligible for Redshift's free tier program, this type of instance will be free for 2 months. So for those of you who want to try out the whole setup after this session, you can check out, see if you're qualified for the Redshift free tier, and you'll be free of charge for 2 months for the exercise of this example. And I'm also going to use a single node, again for this demo purpose, that will be powerful enough to handle that data load. Alright, next step is going through all the different configurations. Here I'm keeping pretty much everything as default other than one particular setting for the network configuration. Here you're required to make the cluster publicly accessible so that the Firehose service can get connected into your Redshift cluster and load data into that. However, that doesn't necessarily mean that you're opening up the cluster to the public, because later on in the VPC security group setting, we're going to restrict access only from the Firehose IP address range. But to make it work, you do need to make your Redshift cluster publicly accessible, and this is a key setting that you'll have to do. Afterwards, I'll review everything to make sure the configurations are alright, then click on Launch the cluster. Then a few minutes later, my Redshift cluster will be up and running with the database created in it. Now we are going to the configuration page of our cluster to modify the default VPC security group setting so that it will allow the inbound access from the Firehose service IP range. So we're going to pick Redshift as the inbound and access rule through TCP protocol with the default port we specified in the cluster configuration. And then we'll add the Firehose service IP range. So depending on the region where you create your Firehose resource, we'll use a different IP address range for the service to access the Redshift cluster. So listed on this slide, we have 3 different IP range for 3 different regions the Firehose service is currently in. So for this example, I'm using the Firehose delivery stream in US East Northern Virginia region. So I'm using the corresponding IP address here. so that the Firehose service is able to access your Redshift cluster for data load purpose. Okay, now we've created Redshift cluster with the database in it, with all the configuration from the networking perspective set up for the Firehose delivery stream to access. Now we are going to connect to the Redshift database and create a particular table there for us to stream the data into. Here I'm using this Agility Workbench tool to connect to the Redshift cluster, but you can use any ODBC or JDBC connection tools as you prefer. And in this example, I'm going to use this following SQL statement to create a table for us to load the streaming data into Redshift. And we'll have to make sure the table structure we create has to match the sample data. Like number of data fields needs to match the number of data columns. The data type for each of the field value within the data record needs to match the column data type for the Redshift table. So this SQL I've modified to make it compatible with the data sample we are going to use today. You can see in the traffic violation data set we have a very rich set of data. For example, time of the stop, time of the incident, the gender of the driver, the geolocation of the incident, and also color and maker of the car, and very rich information, etc. So after I hit this particular create table SQL, this particular table is being created, and I've named it a traffic violation. And you can see if I run a query against this table, it's empty and there's no data set in it. Now we've pretty much set up everything on the Redshift side. We've set up the destination and it's ready for taking the data from the Firehose service and later on for us to query and analyze the data from. Now step 2, we're going to set up the Firehose delivery stream. And the Firehose delivery stream will basically collect the data from the data producers on one side, and on the other side automatically and continuously deliver these data into the Redshift table we just set up. I'm going to the Firehose console and I'll choose Amazon Redshift as a destination I want to use for this particular delivery stream, and I'll name my delivery stream as Redshift stream. And here we have this configuration called intermediate S3 bucket. So for Firehose to Redshift, the service will actually first load all the data into a particular S3 bucket that you own, and then continuously issue a Redshift copy command to load the data from your S3 bucket to your Redshift cluster. And there are 2 reasons for this particular design and setup. Number 1, loading data from S3 to Redshift is still the most efficient way for loading data into Redshift cluster. This way we make sure the data load doesn't use much of the resource on the Redshift side so that they can be preserved for query and analytical purpose. So here I'm using Firehose test bucket. It's one of the buckets that I own for the Firehose service to first streaming the data into. And here optionally you can also specify an S3 prefix, and this Firehose service will attach this particular prefix for all the objects it delivers to the S3 bucket. This is particularly useful for cases where you want to use the same bucket for multiple purposes so that your objects can be grouped logically using this prefix. And for this particular exercise, I'm not going to specify a particular prefix, as the bucket will only be used for this demonstration and example. Then we're going to the Redshift cluster configuration. In the cluster name, I'm putting RedStreaming, which was a cluster we just created from the Redshift console. And so does the database name, StreamingDB. And the table here I'm going to use will be traffic violation. That's the table we just created through the ODBC and JDBC connection tool. Redshift table column, I'm going to leave it blank here because when I create the table, I've ensured that the number of columns within that particular table exactly matches the number of data fields within the data sample. In case you have a mismatch, you can actually specify the columns here so that the service will know what are the columns you want the service to load the data into for this particular Redshift table. Then I'm going to specify a Redshift username and password. Here I'm using the master username and password we just created from the Redshift cluster. For practical purpose, you don't need to, and you probably do not want to use a master username here. You can create a separate user just for the Firehose service to load data into your Redshift cluster. And this particular user needs to have insert permission on the Redshift side so that the Firehose service can use the credential of this user to load data and insert data into this particular Redshift table. On the Redshift copy option, I'm going to use JSON Auto because the sample data we are going to use today is in JSON format. And this option will ensure the Redshift cluster will go ahead and parse the JSON objects and then parse each of the data field to each of the column within that table. We also have a retry duration configuration for the Firehose delivery stream. And the retry duration can be anywhere from 0 seconds to 2 hours. When you configure 0 seconds, that means upon data delivery failure to Redshift, the Firehose service will not retry and skip to the next batch of data directly. So this is a configuration that you can tailor to your particular use case. For example, for use cases where you care about data recency, that you always want the most fresh data to get loaded into your Redshift cluster, then you want to configure low retry duration so that you can make sure that a Firehose always skip to the most recent data if the connection or the data load is failed. On the other side, if your case cares more about data completeness, then you can use a longer retry duration. For example, the maximum retry duration window of 2 hours is normally enough to cover the Redshift maintenance window. So in cases where your Redshift cluster is under maintenance, Firehose will keep retrying and on hold the data delivery until the Redshift cluster is back online. So for this particular exercise, I'm going to use 30 seconds. It's a fine balance between data recency and the completeness. 30 seconds is enough to cover intermittent like network issues, connection issues, but also it's not too long so that I can make sure my data will get delivered after 30 seconds if there's any failure for data load into the Redshift cluster. At the bottom of this page, I think this is a particular useful feature for initial setup purpose. We display the copy command from the Firehose console. So as I previously mentioned, for Firehose to Redshift, the service will first deliver the data into your S3 bucket and then issue a copy command on a continuous manner to load the data from the S3 bucket into the Redshift cluster. So based on the configuration we put in here for this Firehose delivery stream, the service will generate a copy command to match the configurations we put in here. And the copy command displayed here is the exact copy command the service is going to use to copy the data from S3 to Redshift. So in the initial setup phase, it'll be very helpful for us to test out this copy command by using the JDBC or ODBC connection tool to Redshift cluster directly. So this way we can ensure that all the configuration is correctly set up and put in, and if there's any copy failure from the Redshift cluster, we can come back and modify the configuration before we set up the delivery stream. Then we'll click on Next going to the configuration page. The first option here is S3 buffer. So before Firehose delivers the data into the S3 bucket, it can buffer the data records into a certain size or for a certain period of time. You'll configure your buffering options around buffer size or interval. The size can be anywhere from 1 megabyte to 128 megabytes. And the buffer interval can be anywhere from 60 seconds to 15 minutes. And whatever condition gets satisfied first will trigger the data delivery and flush into your S3 bucket. So Firehose S3 buffering feature actually ensures efficient data load into S3 bucket so that number one, we don't end up with too many S3 put API costs, and that will incur a put API call cost on the S3 side. Number two, we ensure that the objects within S3 is not too small so that it will be more efficient for the downstreaming processing. And in this case, it will be more efficient for us to load these objects into the Redshift cluster. Then we'll have S3 compression and encryption option. We can configure the Firehose service to compress our data before we send it to the S3 bucket. And the compression format supported here will be gzip, and that will be the supported data format for Redshift cluster to load the data from S3. And one thing to point out is if we do configure gzip as a compression format here, we'll need to add the gzip copy option in the copy configuration on the previous page so that when the Firehose service issue the copy command to Redshift, Redshift knows that the objects in S3 is gzipped and so that it can uncompress accordingly. And here for this particular session and exercise, I'm going to configure it as uncompress the data to S3. Optionally, we can also specify KM's key for the service to encrypt the data. And if an KM's key is configured here for encryption, upon data delivery to S3, the Firehose service will trigger the S3's server-side encryption to use the particular KM's key to encrypt the data on the S3 side, so that this way your data will be securely stored on S3. Then we'll have an error logging feature. So in case when the Firehose is not able to deliver the data either to your S3 bucket or to your Redshift cluster, it will log an error message in your CloudWatch log group. And you can view these error messages either from the CloudWatch console or from the Firehose console directly, which we'll demonstrate a little bit later on. And this feature is very useful for troubleshooting purposes. So in case you don't see the data being show up in your Redshift cluster, you can come back and check the error message, see what has gone wrong, and you can troubleshoot and fix the issue accordingly. Then lastly, there's this IAM role for security control purpose. This IAM role you will create and allow the Firehose service to access the resource you configured in this Firehose delivery stream. For example, the particular S3 bucket we use here, the Redshift cluster we use here, and in the KM's key we specify if we do enable encryption. This is to ensure that only Firehose service can access these resources you specify here with your explicit permission granted. And also the Firehose service will only have access to the specific bucket, key, and cluster we specify here. Okay. After these two steps, then we'll review all the configuration and settings we put in for the Firehose delivery stream. Then we'll hit the create delivery stream. Then a few minutes later, the stream will be up and running and ready for us to pump the data through. So as you can see, it probably takes about 60 seconds for you to go through the whole configuration and setup for the Firehose delivery stream. And literally after these 60 seconds, we've already had a streaming data pipeline that will continuously load data into my Redshift cluster behind the scene. There's no infrastructure management that I need from my side. Excuse me. And I don't need to provision any server, hosts, storage space, or things like that. All I need to do is this 60 seconds configuration through the console, and all the resource management is handled behind the scene by the Firehose service. Okay, now I've had my Redshift cluster set up, my Firehose delivery stream set up, so I've pretty much already set up a pipeline and the data storage on the Redshift side. Now step 3, it's ready for me to send the data into the Firehose delivery stream. So the sample data, again, as I mentioned here, we're going to use is Maryland's traffic violation data. These data are entered on the cellular device by the police officer whenever there's a traffic violation incident. So this data set is publicly accessible. I've put the URL here so that for those of you who want to kick the tire and try it out later on yourself, you can go ahead and get the data set online. And in this demonstration, I'm going to directly use these data set and parse them and send it to the Firehose service. In a real-world use case, you can imagine that actually these data record will be streamed from the police officer's cellular devices directly into the Firehose service. So as soon as a traffic violation is recorded on the device, it'll be directly streamed into the Firehose service, and later on being able to access to the Redshift cluster within seconds or minutes latency. So this is a sample record on the screen. As I mentioned, it has pretty rich information here. We have the location of this incident, gender, race of the driver, geographic location of the driver, and also the information about the vehicle from maker to color and etc. And in this exercise, I'm going to use a couple of lines of code to parse the data sample and then send them into the Firehose delivery stream. The Firehose service offers 2 APIs to put data into the service. One is called put record. And for this set of API, we'll put each of a single record into one particular API call. And the second API is called put record batch. And as indicated by the name of the API call, we can put multiple data records into a single API call. In this way, you can achieve higher efficiency and higher throughput on the data producer. And for this example, I'm just going to use the single put record API call. This piece of code will parse the data from the sample data and grab each of the line as a JSON object record and then send it into the Firehose service. Now, I've highlighted one particular line, which is to add a new line character behind each of the data record. The reason is because once each of the data record lands into the Firehose service, it'll buffer and concatenate all the records and then flush that into the S3 bucket. So by adding a delimiter, and in this case the new line character, behind each of the record before we send the data to the Firehose service, it'll ensure that after the service concatenated all the data records, we can still distinguish each single record in the S3 object. So after I execute this piece of code and start parsing and send the data records from the sample data into the Firehose service, then the Firehose service will start delivering the data into my Redshift cluster. And as I keep sending these data records to the Firehose service, it'll continuously get the data loaded into the Redshift table that I just created. So step 4, we'll wait for about a minute or two depending on the buffering option we configure in the Firehose delivery stream. Then the data will start showing up in my Redshift table. So now if I run a query from the table, I can see now the data is starting getting loaded into my Redshift table with all the columns that I pre-created. They'll match the data record field that'll be inserted from the data sample. And I can keep refreshing this query from time to time because the new data will be continuously loaded into my Redshift table as they get streamed into the Firehose delivery stream. And we can also do some visualization against the data set once they land in the Redshift cluster. Here I'm going to use Amazon QuickSight. It's the business intelligence tool on the cloud provided by AWS. This service is in preview right now, and I think you can sign up through the website if you want to try it out. So from the service console for QuickSight, I'm going to pick Redshift as my data source and putting my Redshift cluster name, database name, username, and a password for QuickSight to connect into my Redshift table. And it's very easy to set up, and afterwards I'm creating a dashboard to analyze the number of instances by hour throughout the day and also break down by gender. And of course, it's a very rich data set. You can come up with a lot more interesting analysis and visualizations. And on this bar chart graph, it basically shows the number of traffic violation incidents throughout the whole day by hour. And this statistics is from the whole year's data in 2014. And the blue bar are the incidences by male drivers, and the orange bar are the incidents from female drivers. And there are a couple of pretty interesting patterns that you can see. During morning hours, actually there's a pretty large gap by traffic violations between male and female drivers. That's probably because male is still a larger population in the working environment, and in the morning there are more male working population commute to work. And around noon, you can see actually the overall traffic violation starts going down, probably because the drivers have less activity around noon, or maybe all the police officers at lunch break. So now you know when to speed in Maryland. And I'm just kidding, don't speed. Then around afternoon, around 3 p.m. to 5 p.m.-ish, you'll notice actually the gap for traffic violations between female and male, the gap gets smaller and smaller. And that's probably because in the afternoon, the female driver's activity starts getting picked up. So this is kind of a very simple graph that I created. And with the live dashboard, you can imagine as the police officers start booking these incidents on their cellular devices, they'll get pushed into the Firehose delivery stream, and from the Firehose service, it'll continuously load these data into the Redshift table, and this live dashboard will constantly refresh them. You can imagine that throughout the whole day, I can see these bars starting going up and getting populated on my dashboard. And after this session, there are actually some other interesting visualization we can create. For example, we can create a geographic map graph with a heat map setup to indicate the number of traffic violations over time for each of the districts in the Maryland state. And I'll leave this exercise to you guys. You can use your favorite business intelligence tools that you're familiar with to do that. So these are the 4-step setup for us to collect the data from the cellular devices by the police officer. And of course, here we are using the sample data for simulation purpose, all the way to pipe the data into the Firehose delivery stream. And then from the Firehose delivery stream, the service will automatically populate the data into my Redshift cluster and table, then using a business intelligence tool to visualize the data. Then step 5, how do we monitor the streaming data pipeline? As you can see, the Firehose service has tried to minimize the effort from the user side and try to manage as many things as possible behind the scene so that we don't need to worry about many of the setup and maintenance and management. But at the same time, the service also offers a pretty rich monitoring feature set so that we can clearly understand what's happening behind the scene. So first, the Firehose service will offer a set of CloudWatch metrics for us to monitor the data flow. We can, for example, monitor the data from data volume perspective by bytes or by number of records. We can monitor the data flow from the data producer to the Firehose service, and from the Firehose service to the S3 bucket, and then from S3 bucket to the Redshift cluster. We can also monitor the data refreshness so that we know when the data is being delivered by the Firehose service, how much time it has passed since the data is being ingested into the service. And we can also monitor the data delivery success to S3 bucket or Redshift cluster so that we can set up an alarm or alert on the CloudWatch side so that we'll get an email or text message or trigger Lambda downstream workflow when the data delivery fails. So other than the CloudWatch metrics, which tells you if things are working well and which component might not be working well at this point, we also have this CloudWatch logging feature I mentioned previously, which tells you what has gone wrong, and it'll be very rich information for troubleshooting purpose. So in this case, I actually, after I created a delivery stream, I intentionally changed the username and password in my Redshift cluster and using different password. And of course, the Firehose service is still using the old password, and the data delivery will be failed because the service now not able to access the Redshift cluster. Excuse me. And now you can see actually whenever the Firehose not able to deliver the data into the Redshift cluster, it'll book the error message and show up here. So when these kind of issues happen, I can clearly see, oh, the username and the password is not correct, so that I know I need to go to the Firehose console, update my delivery stream with a new valid username and password. Then the Firehose service will recover and start continuously deliver the data to my Redshift table. So these are the kind of 5 steps we've gone through today. So again, I think as you can see, it's really fairly easy to get started with streaming data. So for those of you who are using Redshift today or other data warehouse solutions, chances are you're probably loading your data into these places on a daily basis or maybe hourly basis. Now with the Firehose service on the table, really you can shorten that period of time to minutes or even seconds. And you can see from this session, it really doesn't require any expertise or knowledge on the streaming data sector. All you need to do is create the delivery stream from the Firehose console. Then you can start experiment and using the streaming data pipeline to fill and populate the data into your Redshift cluster. So again, I think after this session, you'll have access to the slides and recording of this session. And you also have access to the data sample that I used today in this session. So I encourage you guys to go ahead and try it out on your site yourself so that you can get a sense of how easy it is to getting started with streaming data analytics on AWS. Okay, and this is the part of the session we'll have today. And now we'll have some time and open up to questions. So the first question that I get on the screen is, where do failure data points end up? For example, if I have the wrong number of columns in my Redshift table. That's a really good question. That's one of the reasons why we have a intermediate S3 bucket. So in case Firehose is not able to load the data from S3 to your Redshift cluster, Firehose will log an error manifest file and send that into your S3 bucket under the error prefix. So whenever there's a data failure to Redshift, you can go to your S3 bucket, look for the error prefix, and the objects that are failed to be delivered into the Redshift cluster will be logged as a manifest file. And you can actually use the ODBC or JDBC connection tool to Redshift to do manual backfill afterwards. So number one, all of your data is securely stored in your S3 bucket, no matter if your Redshift data load is successful or not. Number two, when the data load from S3 to Redshift fails, the Firehose service will log an error manifest file to the S3 bucket to tell you what are the objects that will fail to load. And on the Redshift side, you can actually manually backfill with the error manifest file. The next question is, what is the use of the S3 prefix? So as I mentioned, for all the objects Firehose deliver to your bucket, first it'll automatically append a prefix in time format so that you know your objects will be grouped in a timestamp and partitioned that way. And at the same time, we often see customers use the same bucket for multiple purposes. For example, if I have two delivery streams, one of them used for collecting my web server log data, and the other one I'm going to use them to collect my clickstream data from mobile devices, and I want to store these data in the same S3 bucket. So the prefix feature will be very handy for Firehose service to add this particular prefix before the objects is being delivered to the S3 bucket, so that I know when I log into the S3 bucket, these data will be grouped logically, and I know under which prefix or what kind of data sets. The next question is eventual data delivery guaranteed irrespective of retry setting, or we need to custom code to handle this? So Firehose will retry the data delivery for a period of time that you can configure, anywhere from 0 seconds to 2 hours. And upon the retry duration, if the delivery still fails, the service will skip to the next batch of data and give up on that batch. And the failed data delivery information, again, will be logged into the S3 bucket as an error manifest file to indicate what are the objects that were failed to deliver. And the service currently doesn't handle automatic data backfill, which means for the data that will fail to be delivered, you'll need to do the manual backfill yourself. And often we see customers' implementation to be, for example, we can set up an S3 event to monitor the error manifest file. And once the error manifest file is being delivered to the S3 bucket, it can trigger a Lambda function or a downstreaming workflow to retry the copy from S3 bucket to Redshift cluster for backfill purpose. And you can also run a daily job or an hourly job to scan the error manifest file and do the data load automatically. The next question is the retry at S3 bucket stage or for copying to Redshift? That's a very good question. And the retry is for the copying to Redshift. For data delivery to S3 bucket, we'll keep retrying until the S3 bucket is back online. The reason is because this way we ensure that there's always no data loss. So the Firehose will store the data on the service side for up to 24 hours until these data will be deleted from the delivery stream. So whenever the S3 bucket is not available, or the Firehose service is not able to send the data to the bucket for whatever reason, the service will keep retrying and not give up until 24 hours later the data will be deleted from the delivery stream. The next question on the screen is there a size limitation on incoming data into Firehose? So there are two sets of limitations I think that you can think of. Number one is the limitation for each of the record size. And for each of the data record, we support up to 1,000 kilobytes. And that should be sufficient for vast majority of the streaming data use cases. The second limitation is on the throughput side. Each of the Firehose delivery stream by default can support 5 megabytes per second incoming data volume. And that limit is solved and can be easily raised, but you can just file a ticket with us through the limit increase form and tell us the throughput that you desire, and we'll go ahead and raise that for you. And from pricing perspective, we actually don't charge you for the bandwidth or throughput of your delivery stream. We only charge for the data volume that gets ingest through the Firehose service. If the question is about scale, like how much data volume can the service handle, the service scales extremely well. We can handle data load from millions of devices, We can handle TPS all the way to a couple million TPS per second, and also a couple of gigabytes per second throughput. So again, the service scales extremely well. The next question, where do you define the source for Firehose? How do you define source for streaming data? So the data source really could be anything. For example, an EC2 instance, a web server, a mobile device, an IoT device. And the data source is currently not defined from the Firehose console. So from the Firehose side, you set up a streaming data pipeline and point that into a destination. And for getting data into the service, you'll use one of the two put API calls we provide on the Firehose service side, put record or put record badge. You'll configure your data producer to use these two API calls to push the data into the Firehose service. So you'll run an SDK and a couple of lines simple code on the data producer side, for example, on your EC2 instance, to push the data continuously into the Firehose service. The next question, is there a Java package or something provided by AWS Firehose that can be used by the producer? So other than the two put API calls that I just mentioned, we do offer a Java application, we call it Kinesis Agent. And you can install that on your data producer if it's a Unix instance. What Kinesis Agent does is it'll monitor a set of local files on the instance or servers. And as new data gets written into these files, the agent will automatically pick up these new data records, parse it, and send it into the Firehose service directly and automatically. The agent will also handle file rotation, checkpointing if there's a failure on the instance, and it can also log metrics to CloudWatch for you to monitor the performance of the agent. An example for using the agent, which will be particularly useful, is for streaming log analytics. For example, if you have a set of web application servers, you can install the agent on your web application server, and as the new log line gets generated on the local log file, the Kinesis agent can pick up these new data record. The agent also has a pre-processing functionality. You can configure and convert these log lines into JSON format and do filtering and etc. Then pass that JSON formatted log line into the Firehose service automatically. Then from the Firehose service, you can load that log data in a streaming manner into Redshift or Elasticsearch. The next question is, how long does data stay in S3, and is there any automatic archival and etc.? So Firehose delivers the data into S3 bucket that is owned by you. And the Firehose service does not automatically delete objects in the S3 bucket, which means if you don't choose to delete the data in the S3 bucket, it'll always be there. And on the S3 side, you can set up lifecycle policy to either delete these S3 objects from time to time when the data has been loaded into Redshift cluster, or you can choose to archive these S3 data into Glacier for archival purpose and with a much lower cost for storing these data. The next question, can we use Kinesis Firehose as a real-time streaming analysis platform for custom anomaly detection and alerts? And the answer is yes. So other than Kinesis Firehose, at the Amazon Kinesis platform, we also offer a service called Kinesis Analytics. It allows you to run standard SQL against the data stream and then to trigger an alert or downstreaming workflow. So a very typical setup that you can use, you can stream your data into the Firehose delivery stream, and the Firehose delivery stream will archive these data into S3 in case you want to keep a copy of these data or for other complex batch-oriented analytics down the stream, for example, through a Hadoop job against these S3 objects. At the same time, you can start a Kinesis Analytics application, which will run standard SQL continuously against the Firehose delivery stream. For example, you can do a count of error during the past 5-10 seconds. It'll be a sliding window algorithm on the Kinesis Analytics side. And for example, as soon as the number of errors breach a certain threshold for the past 5 seconds, it can trigger an alarm or alert or trigger a downstreaming workflow on the Kinesis Analytics side. And you can use that for the anomaly detection. It's very similar to the Lambda architecture people have been talking about, where you'll have a Firehose delivery stream. On one hand, it'll archive the data to S3 for batch-oriented workflow. On the other hand, we'll have a Kinesis Analytics application tap into the Firehose delivery stream for real-time anomaly detection. I think these are the questions we have for today, and we're about to run out of time. I think this will conclude our session today. Thanks everyone for attending this session, and I hope you have a good day.